welcome back. So today I'm talking about actually making neural networks with Keras and R. So we built up to this point. We started by talking about basic R programming, went into the advanced features of R, and now we're finally at actually making neural networks. Okay, so to get started, we need to actually set up Keras. If you have an NVIDIA CPU, you may want to take advantage of that and configure Keras to run with that CPU, in which case these instructions are going to be a little bit different. But if you don't have one, or you don't really care about running on a graphics card, or quite frankly, it's just too confusing to get it to run on the graphics card, it feels like the requirements always change, and I personally run into that, then you can just follow these instructions and it'll be perfectly fine. So I've already run these instructions, and if I do it again, it will take extra time and not really serve any purpose in this video. The first line you run is install.package. Actually, install.package. That was a mistake. That's not so. Keras. And that will install the Keras files on your computer. And of course, like I mentioned before, you only run that once for each computer you want to install it on. And after that, you have to actually library Keras, which loads the Keras files you just downloaded into R for them to run. And then you have to run this rather special function, install underscore Keras, install underscore Keras, and then that will fully set up everything you need to have set up for Keras to work. Primarily TensorFlow in the backend. Keras itself does not make and run neural networks. It's actually TensorFlow behind the scenes running these neural network calculations. So you have to do this bit odd thing where you, after installing and librarying Keras, you have to run the install Keras function. If you want to use a graphics card, this is the thing you're most likely going to have to play with to get the version of TensorFlow that works with NVIDIA graphics cards. Okay, so I'm going to go ahead and delete that because I don't want to rerun all that. It takes some time to run, and I don't think running it right now would be all that instructive. Okay, so the main thing I want to talk about with data cleaning is missing data. When you train neural network, you cannot have missing data. It will ruin everything. It won't run. The gradients don't make sense in the context of missing data. So we're going to talk about different ways to address missing data. And this is specifically in the context of machine learning problems. In statistical analysis, you have to be a lot more careful about how you treat missing data, because the act of imputing data increases your uncertainty about the true model. And if you're interested in doing something like that for hypothesis testing, what you really need to do is something more analogous to this, where you use a package like mice to make several imputed data sets and aggregate the errors based on something called Rubin's rule from 1987, and those errors go along with your hypothesis testing. So you would impute the data, fit a model with the data, and then aggregate the results. This pool function here uses a special rule, once again called Rubin's rule, to aggregate errors and give meaningful standard errors and p-values. So this is not what I'm talking about. I'm talking about in training a neural network where we don't have to have this level of uncertainty quantification. So if you're interested in that, this code is provided under the full function in R on my website. It's really helpful, and it just aggregates whatever analysis over a collection of imputed data sets. And that's what you want in that regard. But here, with training neural networks, we don't care too much about standard errors, and we just want results. We want a neural network that will centralize the other data, and if we have a small amount of missingness, we can do things to address that. Okay, so for these examples, I'm going to be using a dataset from the site package. And the data is called BFI. Oh, hit enter, didn't hit control enter. Okay, I'm going to click that. And I want to view BFI. Okay. The BFI dataset is a dataset with 2,800 rows and 28 columns. So these are actually, each row is a question related to one of the big 5 personality characteristics. Actually, I can just do, what was it? Oh, help. I can do help BFI. That's like I would do help for a function, and it will give me information about the data set. So A is agreeableness. I don't want to tell anyone the wrong thing. It doesn't really matter. It's just a large data set for us to do analysis on. I think neural networks on. Okay. Agreeableness, conscientiousness, extroversion, neuroticism, and openness, I believe. So these big 5 personality trait measures are going to be our predictor variable. And we have the outcomes of gender, so are they male or female, education, high school, finished high school, some college graduation, and graduate degree, and age. Besides me being a psychologist and gravitating towards psychological data, actually, technically I'm not supposed to say that. I am a social scientist, not a psychologist, because I only have a master's degree, not a PhD. Anyway, so we have a binary outcome, we have a multi-class classification, and we have a continuous outcome. So this data set's really helpful for capturing the 3 different types of data I'm going to be talking about in the book. Okay, so that's kind of why I pick it, even though we're going to find that these predictor variables are not very good for predicting any of these outcomes, and that's okay. It doesn't really matter how well it does. The concept of what matters. So I still go with BFI even if the personality traits are not all that predictive of gender, education, or age. Maybe they shouldn't be. Okay, so that's our data. And like I always do, I'm going to rename the data. I already clicked on it and made it do that weird thing, but I'm not going to do this for consistency in the code between my code and the code in the book. And just like I talked about, if I do the dim of the data, we get 2,800 rows and 28 columns. So that's 5 sets of 5 predicted variables. and 3 outcome variables. Okay, so you may or may not have noticed that we have missing data. I'm going to go ahead and call view again, because I neglected to actually point out the missing data. We have missing data on the outcomes. Education is by far the worst. So that's a problem, and there's a bit of missing data in other questions. Survey data is inherently filled with missingness, and that's just nothing we have to deal with in this type of data. It's hard to get complete survey data, especially when the questions are sensitive information like, do you do drugs? Or things that people wouldn't want to necessarily say yes to, but they also wouldn't want to lie about. So, inherently you have missing data in survey data, and sometimes in experimental data, unfortunately. Okay, so one thing we can do is simply find all the rows that don't have missing data and get rid of every row that does. That's called listwise deletion. And you can do that fairly easily by using the complete cases function to identify the rows that have complete data, and that will get you what you want. And if we do dim of this other data set, we will get a different result here. So we had a little bit less than 600 rows deleted just by eliminating missing data from the rows. So the problem with that is you lose a lot of data, obviously. If it's 1 or 2 rows, it doesn't really matter, but if you have significant missingness, then you might run into problems with training your neural networks, and you lose a lot of information. If you think about it, we had 27 observations and only 1 missing observation, but we threw out all of the 27 observations simply because 1 was missing out of the 28. So you may think about imputing data, and we're just gonna go through that real quick. There's probably a custom function to do this in some package, but it's actually good practice for function writing. Because not everything you're going to want to do has a function made for it. Okay, so a common thing to do is replace the values with an impossible value, -99. Oh, I put parentheses, not the curly bracket. Let's go back. Okay. So we're just doing a nested loop here. 1 in row data frame, and this is a good reason why hard coding the number of columns and rows is a bad idea. Because I want this to work for any arbitrary data frame, not just a data frame with a predefined number of rows and columns. That's not very helpful. Okay, so this is going to iterate through all the rows and columns, and this is the test to see if there's a missing value. It's .na. So data frame I comma say. I is the row, say is the column, and then we go over to equal true. Now we decide what to do with it. And what we do is say data frame. Nope, that's data dot frame. Love that. Data frame I comma k equal that value that we specified for representation. Okay, now we go down to the last line and we say return data frame. If we didn't specify that, I don't know what it would return, but it may not necessarily be the data frame. Okay. Okay, now we have the function right here. Let's test it out. ML data 99 equal value invitation. If I were doing this with no network data, I probably would not pick negative 99. Maybe you have a meaningful missing value. Like missing data would be a 0. That would be a good example of when that would make sense. So I run that, and I'm going to do view ML data 99. And now we're going to see when we go to that education column that had all the missing data, we have a whole bunch of negative 99. Perhaps 0 would be a better default value. Perhaps some other value that makes sense for your data would be a better default value. It really depends on the situation you have. Okay, and now we can do the same thing, but with mean imputation. We don't have to rewrite this whole function, because I don't think that's a good use of time. So mean data frame comma a. The na.rm it's not optional here, because if you don't put na.rm, it will find the missing value and refuse to run, and that would not be helpful to you. Clearly, it would just be, it would fail to run because it's going to try to take the mean of a column with missing data. Okay, so ML data mean. Alright, maybe I can click that. Nope, I made a mistake. I clicked on the function, not the data that it created. There we are. But the problem with this is we have now nonsense imputation. There's no value of education at 3.19. It was whole integer values, and that's a slight problem. I know mean imputation is commonly used, but mean imputation kind of ignores the relationship between variables. It doesn't matter what these variables are, this new value is not the mean. I know people like to do it. I dislike it in this application, and I especially dislike it if you're doing hypothesis testing. But I know it's something people like to do, so I included it. If you want to get more sophisticated, you can use a package like Amelia to make a bunch of likely imputed datasets using the EM algorithm and aggregate them. I am going to probably avoid doing that for the sake of time. I think I will. I'll do one. I'm not going to write out this whole function, but I'll tell you what we get. Okay, so library Amelia. Okay. Amelia output. You could also do the same thing with mice. Mice might be a little bit more flexible. No, I don't want unimputed data. I want my data. I want BFI. BFI. Or ML data. I guess that would be the more consistent way to do it. ML data. Number of replicates. M. Let's do 5 replicates. Whatever. And let me show you what we get out of this. So we get a list, a mini function output list. And then we have imputation. And we have 5 complete data frames. I'll go ahead and subset this. So first data frame, whatever, Amelia output. I believe we can do money sign, yep, invitation, and money sign M1. And theoretically, you could do this. You could just impute one data frame and use that. I think even this would be a better idea than mean imputation. So if you want to do that, you can just set M equal to 1. Get Y make 5 data frames when you only need 1. And this would be a somewhat reasonable imputation method for missing data. Or you could, as I said, make a whole bunch of imputed data frames with likely values based on the EM algorithm and aggregate them, as I've done here. Either way is an option, and either way is totally fine. Okay, so I'm going to go ahead and skip this. And we're going to start talking about data separation, like training and test data. Okay. So to make this the same as what you do, I'm going to set my speed. Now I need to decide how much training data I want and how much testing data I want. When you shouldn't test your machine learning models on the same data used to train them. That's how you get inflated accuracy metrics. I could train a highly complex model on my training data, and the loss value would be extremely low or 0. That's one thing you have to watch out for, and that's why we subset data in the training and test. The sample, all it does is data Amelia. I'm not going to do Amelia because I don't even have Amelia. I'm going to go with the list-wise deletion version. We lost some data, but it should be the best quality. Or actually, never mind. I'm going to do the first data frame I made. That should be a very reasonable imputed data set. So we're going to go with that. Replace equal T. I'll go to the next line here. Prob equal. So the probability of getting a 1 is the desired training proportion, and the probability of getting a 2 is just 1 minus that. So the entire probability is the desired. Hopefully I just typed this out right, because it's not testing name. Okay, so let's try that. Okay, so it's not mad at me. And in the book, I have to take the first 10 to tell you what we got. A vector of 1 and 2. You needed to replace equal t or true. If not, you would just, I'll show you. It will throw an error. It's going to sample a 1 and a 2, and then not have anything else to sample. It gets very mad. So you have to go back and say true. Okay. Well, let me set the seed again so I get the proper seed. Although my results will not match what we have in the book now because I did not use the same data set. Training ML. The first data frame. Where end is equal to 1. We pull those values, and I'm dropping the 28th column. I'm dropping the 28th column with the 28th column is aid, and the first example we're running is the continuous outcome example. So we have training data, and now we have test data. And I have to really resist here not to copy the code in the book, because we are using a different data frame here. Minus 28. And now we need the training target and the test target, which is just the outcome we want to predict. So that's going to be aid, target, and so first data frame, end equal 1, and instead of minus 28, it's going to be only 28. Test target. Oh. Okay. First data frame end equal 2, comma 28. Okay. Okay, so now I'm going to delete some of this code, because now I have my training and test target established. I don't really need it so much. Okay, so we want to standardize the training and test data to make the neural network converge more easily. Instead of having a wide variety of values, it's going to be restricted. So, and we do the standardization based on the mean and standard deviation of the training data, not the test data. The test data is data we theoretically we have never seen, and therefore we cannot use to do any of these calculations. So what I did here is use the apply function to take column means. So that's just the mean of every variable. And then I'm going to do the same thing to get column standard deviation. And we're going to be scaling based on the mean and standard deviations in a second. So training, comma 2, comma FB. So training. So we are overriding the current training variable, the scale, and that's a Keras function. Training center equal training mean, and then scale equal training standard deviation. And that went off a little bit, so I'm just gonna pull that in and rerun that. And then test is going to be overridden 2 and scaled not on its mean and standard deviation, but on the mean and standard deviation of the data we have now. The training mean and standard deviation. Okay, now we've made our data. And we're going to actually start doing neural network creation. Okay, so I've already libraried Keras, and I don't need to do that again. Okay, so model, Keras, model, and it's not popping up. I misspelled something. Let me try that again. Did I library Keras? Now I'm second guessing myself. Library Keras. Okay, so let me go back and try this again. Clearly I didn't. Okay, so you start with Keras model sequential. And that basically initializes the neural network model that we're going to build on. Okay, so now there's a model, and I get a whole bunch of warning messages. You can just ignore them. It's basically telling me it's not set up to run on a graphics card, it's running on CPU, and it's going to be slower. And that's okay, because we don't need anything too big here. I'm going to go ahead and delete my previous code so I can have extra space for my neural network here. Okay. So every time we add on to the model, we have to use this operator called a pipe operator, and it essentially how to describe it. So this pipe operator is used in tidyverse code, and what it says is take this right here and put it as the first argument into this function. And then this whole thing right here, we add it as the first argument into this function, and so on. You don't need to think of it that way. You can just think of it as that's the operator we put in between neural network layers. Okay, so a normal layer in the syntax is layer dense, or it's also called a fully connected layer. So every neuron in one row of neurons is connected to every neuron in the next row of neurons. Okay, so we have units. So that is the number of neurons in that layer. Not in the input layer, just in that layer going on to the next one. So in the book I specify 60. Activation is going to be Relu or Rulu, and that is a function that adds nonlinearity to the neural network. If we only had these layers without activation functions, we would actually just have a complex piecewise linear regression, which is not what we want. So only on the first layer we have to specify the input state, so the number of columns in our data frame, and that's going to be 27. And I think I might get cut off a little bit, but let's know that it's the same operator as before. Actually, I'll just back it up so I'm not cut off. Okay. Ooh, that looks bad though. Normally it's offset a little bit, and I want to keep that formatting. Okay, so to add more layers, let's do it again. So now I want a layer with 30 units and the same activation. And it's basically what you might call a hinge function. Everywhere that it's negative, the value is set to 0, and everywhere it's positive, the value is set to itself. And when I finish typing this out, we'll talk about why I chose these numbers of units, because that's important too. Relu. There's one more now. Layer dense unit equal 1. Oh, I think I made a mistake once or twice. That's not a unit, that's a unit. And I made a mistake again, trying to fix my mistake. Okay, so here's what the neural network does. It goes from an input of size 27, balloons out into size of 60, and then it gradually tapers down to the final input of 1. And each layer here gets a Relu activation, except for the last layer. If we did it to the last layer, we'd be saying make every output positive. And that's not really what we want. We don't care if it's positive. We just want it to do a good job regressing on the continuous variable. The continuous variable of age happens to always be positive, but we don't. We gain nothing by imposing that limitation. It would only serve to make it more complex. Okay? Let's run that. And now we have to do what we call compile the model. And for our purposes, it's basically telling the model what metrics we want to use to optimize this neural network. So we're doing a regression, so we want MSE, or maybe I'd say we were regressing on a continuous variable and we want MSE. And the optimizer, it's really not going to matter too much here, and Atom is a perfectly fine option. and then we just have metrics. We can track MAE. I'm actually not going to bother. I think you might think clutter up the plot. And I would just have one more step, and that to actually fit the model. So history, because that variable will also hold the training history, and that's why it's called history. So fit, and then now we actually provide the training in training target. Training, comma, training target. So it's literally x comma y. So epochs is the number of times the entire data set is fed through the model. And we want a large enough number of epochs to capture the relationships in the data. Batch size is the number of rows input in the model before the gradient is calculated. And normally that's in base powers of 2, so 16, 32, 64, 128. We're picking 32. And ultimately, what that's going to determine is how quickly the model converts to the solution. It's not going to be too big a deal. And we also have an option of validation split. So this training, the training data will have some extra data held back as another test to make sure we're not over or underfitting the model. Did I run compile? Yes, I did. So when I run this, it's going to start training. And we get a plot. So the training loss is the blue, and the validation loss is the green. And as we can see, as we get further down, they converge to the same line. And maybe I'll go ahead and do this again with a larger number of epochs to show that when we overtrain the model, the actual loss, the blue loss, the loss defined by the training data can go to 0, while the validation loss will not. Because it's overfitting to the data. It's not capturing true relationships, it's capturing noise. So I'll go ahead and do 30. And I think I might have specified this in a way that overfitting is unlikely. It's not that big a neural network. Oh, and it's growing. That's perfect. So this is an overfit neural network. The validation loss is even increasing at the end, while the loss on the training data is going to 0. And it will go to 0 in a sufficiently large neural network. That's just what it does. And when I refer to loss, I'm just talking about the mean squared error between the actual value and the predicted value. That's what we're talking about there. Okay, so I'm going to go back to 10. And oh, that still looks rough, actually. What's going on here? I'm gonna try running the whole thing again. I think it's because because I kept fitting, and it did 10 more epochs, 10 more epochs. And I needed to run all the code again, so that was my mistake. I'm gonna do this again to show that I'm not creating, that it will in fact diverge. Okay, so this is a better representation of what I'm talking about. Once again, it still diverges here, and it will diverge because the neural network will fit arbitrarily well to the data. Okay. No. We get the plot. We don't have MAE because I did not specify that additional metric there in the compile step. So if you use summary of the model, we can see the number of parameters in the model, 6,422, and the actual model architecture. Oh, did I mess up? I think I might have inadvertently added that twice. Yeah. Yeah, because I did not, when I reran this, I did not include that. So what it did, it took the model, added more layers, and so on. But still, it will diverge. Maybe I could actually do 50 to highlight that better. Or you could believe me. Okay, so let's keep going. And it's diverging. Sorry about that. I am really missing the mark in rerunning these models. Okay. So we get exactly what we got in the book. And it's 3,991 parameters. Still more than enough parameters to overfit a model. Okay. So we looked at the training data and the validation data. But how about the data that was never in the training, the test data? And we can evaluate how well that did with the evaluate function. So test, comma, test, target. And the loss is pretty much dead on the other loss. And we can do even better. So we're gonna look at the model prediction. Model predict test, and that went almost instantly. So that's the real value, and this is the model prediction. And I'm going to add avline. It should have a slope of 1. It should match. And that's what you get. So it's not perfect. But as I said in the beginning, the personality traits are not all that predictive of age, education, or gender. Okay, we can also compare the results to linear regression. I am actually going to try to avoid doing this because I think that might distract from what we're doing already. Okay. But it is, of course, a good idea to compare a neural network to just regular linear regression. Okay, let's delete that too and go back to my environment. I'm going to go ahead and rename actually the data that we've been using to ML data Amelia. And it's actually not really a lie, because I did make it using Amelia. It's not in that same way. Okay. Now I can pretty much copy the code, and that's going to be really helpful. Set.need. And pull again. And there are countless numbers of ways to subset data. This is just the way I chose to in the book. As long as you don't end up crossing your training and test data. That would be not good. And here I just hard-coded the probabilities. Okay, so we're doing the same type of stuff, except now we're taking out the 26th column of Cinder. And that's what we're going to be doing the regression on. Or making the neural network for making the model. I've been taking a course that talks a lot about logistic regression, and I think that might be where I got that from. Training, test. It's not a bad idea to clear your environment between these, so you don't end up accidentally reusing an old training and test. Because I'm literally calling these the same thing, but it's probably ill-advised. But I don't want to delete that. I don't want to clear my environment, because if I did that, I would lose my ML data. Training target. ML data Amelia index equal 1, and then I only want column 26. Test target ML data Amelia index equal 2, and I only want column 26. Oh, I also decided to recode this. Training target, I believe in the BFI dataset, men are 1 and women are 2 or something like that. Let me look in the BFI dataset. No, not what I wanted. I want to view it. Okay. Yes, we have 1s and 2s. I want 0s and 1s. And that's why I recode. I believe I coded women are 0, men are 1. So, a 1. So, for Cinder, a 1, comma 0. What on earth am I doing? Oh, I went ahead and coded. That's why it... Yeah. That I do it down there. Okay. That's why. The one hot encoding is you have one variable indicating one category and one indicating another. So we have 2 separate variables, one for male, one for female. And yeah, that's reflected in the neural network architecture. Okay, now that that's cleared up, let's get back to coding. So I'm recoding it to 1 and 0, which is required by the two categorical functions. And I'm doing it with the if-else function. So you have a condition, training target equals some condition, so 2. Then it is 0. And then if that's not true, it equals 1. So if true, 0. If not true, 1. Then I have to do the same thing for the test data. And this is really stuff that will play nice with the two categorical function. Not necessarily a hard requirement in general. And once I don't know why I ran that one code. It all needs to be run in one go. One line of code. Training. And now I'm doing the same thing, standardizing. On the sorting it M and S, mean and standard deviation. There's clearly a function called column means I found that it gets the means of the column for me. But I still need to use apply for the standard deviation. 2, SD. When did I calculate SD? Oh no, I don't need to. That's a function. And I am flipping. Okay. Okay, so training. Scale. Training, NJ equals M. And SD. Scale equals F. And then test at the same thing. Scale, test, NJ equals M. Scale equals S. And now, we need to do this one last thing. Target to categorical. And if want training, target, and then test target will be the same thing. To categorical test target. Okay, now I need to run all the code. Okay, so I want training target. Okay, so we have two columns, 1, 0, 1, 1. And that's going to represent males and females. So that's going to explain what I wrote in the book. So speaking of which, okay, so within a 1, 0 would be female and 0, 1 male. So that's male, that's female. Okay? And this is called one-hot encoding, and we use it for categorical variable. Okay, now I can finally get to the neural network. I'm just going to delete all this code. You wouldn't, but I will, because I'm making a video. Keras. So we initialize the Keras model. we add on to it. Oof. Alright. The layer dent, the standard layer type unit equal 15. Activation equal true. Nothing new here. And for the first layer, but no other layer, I need to specify input tape. And we do it just like that. And I can't help it. I'm going to the next line. Okay, layer didn't unit equal 15. Activation equal ReLU. So this is very similar to the regression. The only difference is how we prepared our data with the one-hot encoding and what we do to the last layer of the neural network. And this is the last layer of the neural network. No, it's not. I have one more. Okay. Unit equal 15. Activation equal ReLU. Now, okay, so our output is in the form of two columns, so we actually have unit equal 2, and the activation is going to be different. It's going to be softmax, which restricts the output to between 0 and 1. So the probability proxies now. Actually, I think it means I think it actually might restrict the output of all the units to being the sum of 1. Actually, I don't think it restricted from 0 to 1. I think it has to be the sum of 1. We'll look at that when I run the model. And I just noticed I did the same thing where I said unit, not units. So let's fix that. I don't know if it would actually get mad at me, but I don't want to find out in this video. Okay? Now I need to write compile. Nope, need model. I read the comment and started typing that. Compile. So loss is going to be different. It's going to be binary cross entropy. Hope we got that spelling right. You'll probably throw an error if I didn't. Optimize is still going to be Atom. I'm actually going to put it on the next line. Alright. And we want the metric of accuracy. Put on the next line too. Don't know why I ran that, nothing else, but let's keep going. I'll just have to rerun all the code. I can't believe I kept messing up before adding on to the model. I think it's harder to do things when you're recording yourself doing them. Training. Kind of talking code and everything. And there's no hard and fast rule for the number of epochs you need, the bad side. These are called hyperparameters, and you kind of have to play around with it and see what works for your specific application. I haven't defined that these parameters work for my application, but it can definitely be a game of trial and error. Okay, now I need to run all of the code here, and we're training. Oof. So the lock went to 0 very quickly. Oh yeah, that's good. And the accuracy started going up. So the validation accuracy did not go up too much here. I'm gonna try it with more epoch. Well, this might be all we get, honestly. Let's see though. I'm gonna try it again and go to 25. But I might just overfit the model too. This is part of the game of trial and error. Yeah, the validation accuracy is not going up very much. And every time I rerun it with different hyperparameters, I am incidentally influencing the validation accuracy. That's why the validation accuracy is not enough. And everything I do kind of leaks into the accuracy of the validation. Okay, so this may not be all that predictive, but it does train up a little bit. I might would increase the epoch and implement some methods of getting the model to not overfit as much to see if I could get a better outcome. And I don't know which one I choose in my section about overfitting, but we might get there. It might be this one. Okay. And I'm going to go ahead and evaluate the accuracy on the test data that we did not train on. And it's going to probably be a little bit different because I use more epochs. And the data set's different. And it's always going to be a little different too, because the neural network training is stochastic. You will never get the same training every time, because the weights the neural network starts off with are themselves random. Okay. We actually got a little bit better in accuracy, but barely, and that's probably just random noise. Okay. So now we're doing multiclass classification on that education variable. So I'll go back to my environment, clear everything out, clear this model out. Let.seed. End sample 1, 2 in row ML data million. This is going to be a really long video, but I think it'll be useful. Zero point 0.7, 0.3. I'm not going to pop that down to the next line. Okay, so training is now going to be ML data Amelia. And if you don't have to delete your code like mine, you could just modify it to reflect the new things. So we're getting rid of the 27 column, which is that education column. Test equal ML data Amelia index equal 2 comma negative 27. Training target going to be that same thing. Maybe if I didn't hate myself, I'd do more copying and pasting. And I'm subtracting 1 because I want the categories to start at 0 instead of 1. So I'm just recoding it in a simple way. Test target equal ML data amelia index equal 2 comma 27. This is probably going to be longer than my 1 hour video yesterday. But we're getting done with the book. I'm excited to start on my second book, making the videos about that. About a system of neural cryptography, hiding messages in a matrix, encoding them and decoding them with a neural network. I was happy with it, but it hadn't really taken off yet. Maybe it won't. That was my cat, if you heard that. I know a prior video I said that was my cat, and I'm pretty sure no one heard that except me on the video. But I kept it. I'm trying not to edit my videos as much. Some of you had to take a lot of time, and I feel like I can be overly critical of my own work to the point of obsessing over it and trying to edit out pauses and things like that. Okay, so we're doing one hot encoding again. Training target. That's why I had to subtract 1 to appease the 2 categorical function. Training target. Test target. 2 categorical. Test target. Okay. Okay. So now we have 5 columns, 1 for each education status. So that's the lowest education, that's the highest education, and going down. Alright. So let's make this neural network. And this structure is very similar to the regression one. You know what, I don't know if I ever actually looked at the outcome of that previous regression model. I keep saying regression. The previous neural network model. The softmax. Yeah, didn't think it'd be that easy. I think, now that I'm remembering, I think softmax makes the total output of this layer sum to 1. So it's the probability of one outcome versus another. Okay. Sorry about that. Let's get back to this one. Okay, so if we start out every one of them, Keras model sequential. And that's just initializing the neural network. And we have to make the neural network. Layer dim unit 30 activation ReLU. And you have other activation function choices. You don't have to do this. There's different reasons why you might want to use a different activation function, and they're valid. But ReLU is very often good enough. It's something you don't have to think about too much. Just like the optimizer atom. Okay. Unit equal 20. So we're starting off big and tapering down, just like we did in the last one. ReLU. Layer 10. Unit equal 15. Activation. It's ReLU again. Okay, now it changes right at the end. Now we don't want ReLU, we want softmax. And is that what we used last time too? Yeah. Okay, I'm pretty sure it makes the column add up to 1 in your prediction output. That feels very right. I misspoke before, and it does not make the individual column be restricted from 0 to 1. Okay. The model compile. Loss is going to be a new loss function called categorical cross entropy. The old one was binary cross entropy. What we're really looking at is, do personality traits predict education level? Which might be a meaningful question. Atom. Metric. We want accuracy because we're doing a classification task. And categorical cross entropy is not all that meaningful. And almost done. History. Oh, goodness, what did I do? Okay, the model. We want to fit on our training data. Training target. F5 equal 20. Bat size equal 32. And validation spread equal 0.2. Oh, that's 3? Okay. Ooh. That loss went down very quickly, but the validation loss did not. Meaning we're fitting the noise, not necessarily the relationships in the data. You can see that in the accuracy too. Loss goes up, validation accuracy only maybe marginally improved, but not really. Okay. I think the reality of this data is personality traits are not all that predictive of gender, education, or age. This is an evaluation on the held back test data. Ooh, and it's really mad at me. What have I done? I may need to restart R. I hope not. I think this might just be a newly developed error. Okay, let's just assume it's close to that. And I'm going to session restart R. Library Keras. And really hope this works. What must be a function or character string? What have I done? Model. Evaluate. Test, comma, test target. Oh. I made a mistake somewhere. It is not a problem with R, it's a problem with me. I did not. No. No. Oh. Ooh. No, that's not right either. That's the old one, that's regression. Okay, I did not know why that's not working. And I definitely see some need to debug. I'm gonna leave it alone. It's probably not all that dissimilar to this, and I don't know why it's not working. Yeah, they got a test data that, yeah. Yeah, I don't know why it's not working. Okay, so let's go ahead and move on. Yeah, because it was the right input. I'm getting kind of tired. Set not seed. So we're looking at methods to prevent overfitting. Because that's the main problem. Well, that's a main problem we have. We have a model with infinitely much flexibility. It can fit any pattern in the data, even random noise, and we want to prevent that. And hopefully I don't have problems like that again. I don't know if that was me or a bug. Okay. So in this example, we're taking out column 26, which would be Cindy. And we did have an overfitting problem with that. This may really help fix that. Data amelia. And that equal 1, comma, negative 26. Test ml data amelia index equal 2, comma, minus 26. Yeah, I don't know what I did wrong. Or did anything wrong. I really have no idea. Training. Target. I'd definitely look at it more if I wasn't trying to get this video done. Although it could sometimes tends to flow behind the scenes and throw an error, and it's not really clear why. Or maybe I did something. Okay, promise I'm almost done here. Training. Target. I have to recode them just like I did before. Training. Target. Equal 2, comma, 0, comma, 1. You know, what it might be mad about is the fact that the test target, the actual, yeah, the ML data amelia, it had weird values for education, like 4.1. That might have not gotten processed by the 2 categorical function very well. And I probably should have rounded those values off to get a better data. That might be the problem. I don't know, because I haven't tested it, obviously. Test target equal 2, comma, 0, comma, 1. And now we gotta do the standardization. Sometimes you don't necessarily need to standardize, but it's a good idea. Especially if you have highly variable data. Training equal scale training, comma, center equal m, comma, scale equal f. I hope I don't run into that same error right at the end of trying to do the test. Center equal m, scale equal f. And now we did have training target to category. Oh goodness, 2 categorical. Training target and then test target to categorical test target. Okay, everything ran. Okay, and I'm actually going to cut here. Lord forbid I have to do all this again. I will try not to have to do all that again. Okay, so model sequential, that everything is, you always have to do that. or custom, but that's a more advanced thing you'd have to learn how to do. Okay, so one method of preventing overfitting is using dropout layers. What dropout layers do is they randomly select a proportion of the neurons to be deleted in training. This forces the neural network to identify patterns and have a more diffuse representation of your data. What this really means is that it helps reduce the noise being trained on. The layer, then unit equal 30, activation always ruler, unless you have a good reason not to. Input save equal 27. And we have the pipe operator. Okay, now we introduce this function called layer dropout, and the rate is the proportion of neurons that are quote unquote dropped out or deleted, however you want to think about it. Layer then unit equal 30, activation ruler. Yeah, I need to fix what I did. Comma activation ruler. I needed a shortcut to insert the pipe operator. I don't know it offhand. Rate equal 0.3. I like to start high in the dropout and decrease. That also goes along with the architecture of making a wide initial node network and tapering down. You wouldn't want to add 2 dropout layers in a row. Okay, so where am I in this? Unit equal 30, activation. Goodness, I started doing it again. Activation equal ruler. And then the last dropout layer we're going to add rate equal 0.2. The last layer can never be a dropout layer. And then you just be deleting some of your output columns, and that doesn't make any sense. You wouldn't want to do that. So it's 2 because we're one hot encoded. And the activation softmax, we're working with a categorical variable. Softmax. Okay, and everything else is the same. Compile. Log, name log, binary cross entropy. Cross entropy. I'm going to go down to the next line. Optimizer. We're going to use Atom again. And then our metrics are going to be accuracy. Because it's more obvious what we're talking about when we're talking about accuracy compared to, honestly, whatever binary cross entropy is. I don't actually no offhand either. So history, model, fit, training, comma, training, target, and now we add the hyperparameter epoch equals 30. I can add more epoch because we are adding things to reduce overfitting. Oh, okay. Let's run all this now. Wait, is it mad before it even gets to the compile step? Yes, it's mad about the neural network. I'm an idiot. I know exactly what I did. Goodness. Model. You get so far ahead of yourself. Okay. Let's move on, guys. Sorry about that. And let's run now. Okay. Okay, so still overfits a good bit. Maybe not so bad like that. I am so mad at myself. And that's okay. Let's try to do this more heavily here. 0.5, 0.4, no, 0.4, 0.3. I don't need to run this whole thing, do I? Whatever, I'm gonna do it anyway. It still overfits substantially. We're gonna really stack it up then. No. If you do too much dropout, it won't run at all. It won't optimize. It's close to here. See the losses going together. The true problem here is not that. Oh. Goodness. I forgot my face is covering down here. Okay. So what I was doing was increasing dropout. But that didn't necessarily reflect in the loss invalidation loss converting. But it helped. Okay. So now we're going to implement early stopping. Another thing you can do to prevent overfitting. And I'm going to drop the dropout rate down back to where it was. Okay. So what we need to add is a callback called early stopping. So we need to specify it here. Early stopping. I'm so mad I messed that up. It's so easy to make a simple mistake that breaks everything. Monitor equal validation accuracy. And this is another way your validation data can leak into your training data results, and why it's not enough alone. Patient equal 10. So what this does is if the validation accuracy does not increase after 10 cycles, it will stop early. And we're going to increase the epoch to 50 to have that be reflected. And we need to add a callback to the model fit. The callback we don't specify right here. So callback, early stopping. Okay. Let's have that run. Okay, so it ran for 32 epochs out of 50, and it stopped after the validation accuracy did not increase. So that's one way to stop overfitting, because if it hadn't been stopped, this loss would have gone to 0, while the validation loss would have stayed the same. Or it would have gotten worse. It can definitely get worse as the training data is just so overfit to it fits to the noise is what I'm trying to say. So you can stop it early. You can also reduce the learning rate on plateau, and that can try to get a little bit more accuracy out of it. So callback, reduce learning rate. So when you get to somewhere like here, the learning rate will drop just a little bit to try to get a better accuracy. Okay? So I haven't... Oh, yep. Reduce learning rate on plateau, and we have a few arguments for that. So we want to monitor the validation accuracy. Okay, so val accuracy. This video is gonna be like 2 hours. Especially if I don't cut out my mistake. The factor. So how much we want to reduce the learning rate by. And I'm gonna say 0.95. And the patient, how long it waits to do that. How long does it have to be plateaued? And we're going to say 2. And now we need to go down and modify the fit. And instead of 1 callback, we are going to have 2 callbacks. So C, comma, reduce LR. And then I need 1 more print. Okay. So let's get a little bit better out of it. Better result out of it. And we end up with another graph showing when the learning rate was reduced. Okay, so it stopped early at the 39th epoch. And this showed you every time there's a reduction. And it might have gotten slightly better. Okay, so we ended at a validation accuracy of 0.67. Last time we ended at a validation accuracy of, that's embarrassing, 0.67. And before that, 0.64, so we did a little bit better. That's another technique to try to use in your training. Okay, and I have a conclusion written here, and that's the end of the book. We've gone from knowing nothing about R programming to writing somewhat complex neural networks. Alright, that's the end of the video and the series. Thank you for watching.